Hello everyone, welcome back. This is lecture 5 of the course Introduction to Semiconductor Devices. In the last lecture, we introduced a few concepts like effective mass, and we introduced intrinsic carrier density, and then we talked about how doping can be used as a means to control the carrier density in semiconductor devices. And in the end, we also studied a little bit about the temperature dependence of the carrier density in an intrinsic semiconductor as well as an extrinsic semiconductor. So today, we will try to get into a little bit more depth. We will try to give you a quantitative picture of what's happening. Okay. So to start with, we have to introduce a few functions, a few concepts. So the first one is Fermi function. Okay. Fermi function is a function which is given here. It's essentially 1 over exponential 1 over 1 plus exponential e minus ef by kt. Okay. So this is a function that gives you the probability. So f of e gives the probability of finding an electron at a particular energy, an electron at a energy E. Okay. Why is this important? Well, because electrons are distributed. We have these energy bands, which are the allowed states, but there is a certain amount of probability of which of them will be filled, which is not filled. So that probability is given by this Fermi function. So it plays a very crucial role. Okay. And in this function, kT is anyway the Boltzmann constant, and then temperature. So that will be units of energy. And EF is what is known as Fermi energy, or you can also call it Fermi level. Okay. So EF is a number, basically, and an energy. Okay. So how does this function behave? Okay. Let's try to analyze the situation. So let's consider, to begin with, let's say it's easier to do it at T equal to 0 Kelvin. So let's consider that. Okay. So when T equal to 0, temperature is 0, what happens if energy is less than EF? E is less than EF. So EF implies this here, the exponential term in the denominator is going to be negative, right? So exponential E minus EF is in the denominator, and this term will be the exponential's term in the exponential is going to be negative, and because of which essentially the exponential will go to 0. Okay. Therefore, your f of e, the probability of finding finding an electron at a particular energy, if E is less than EF, okay, that is going to be 1. Okay, it has a very high probability of finding an electron below an energy EF. Okay. Now, what happens if energy is greater than EF? Okay. So if E is greater than EF, then this exponential term is the most important again. So now this is going to be E minus EF. So the numerator is going to be positive, but then the denominator is going to be very small, right? So then essentially this kind of goes to infinity, right? Tends towards infinity. Therefore, f of e is going to be 0. So Fermi function at 0 degrees Kelvin behaves like a step function. Below EF, it's going to be 1. Above EF, it's going to be 0. What happens at EF? Okay. So for a moment, consider E equal to EF. Okay. When E equal to EF, exponential basically the parameter in the exponential is 0. That means exponential of 0 is 1. So basically f of e is going to be 1 over 2, half. So it's going to be exactly 0.5, right? So this is an important thing to note. So whenever your energy equal to Fermi energy, then the probability f of e is going to be half. So this also gives you one definition of Fermi energy. Is basically you can define it as Fermi energy is that energy where f of e is going to be half. This is one definition of Fermi energy. All right. What happens at higher temperatures? Think about it. Okay. So if you look at the expression for Fermi energy at E equal to EF, you saw that it is basically independent, right? Independent of temperature. So this particular thing, this basically is independent of temperature. Okay. So f of e is going to be half no matter what the temperature is. So if you analyze it and you can plot it in MATLAB or Python, it looks, the graph is shown here. It looks like this. So here I have deliberately, flipped the axis. So I'm plotting f of e along x-axis, okay, and energy along y-axis. Okay? There is a reason why we do that. Anyway, what you see is at t equal to 0, you have this step-like behavior. Okay, at higher energies there is no probability. At E below EF, it's going to be probability of 1. Okay, very high probability. So now, as temperature increases, the probability gets stretched. But always, the f of e should go through half at EF. Okay. So if you keep the EF constant with change temperature, it's going to stretch like this. And if I, for example, if I take one more, case where let's say I take a slightly higher temperature, so that would have been like this. It will stretch out further. Basically, this will be T equal to, let's say, 400 Kelvin. So as you increase the temperature, the Fermi distribution stretches out. Okay. So you can make a note here. So basically, as T increases, f of e is stretched around EF. Okay. So this is a characteristic. Okay. Fine. So how does this help us? Well, this definition of Fermi energy is useful in denoting the operation, in actually representing the operation of various semiconductor devices. For example, when we talk of PN junctions or MOSFETs, we'll always show a level which is called as Fermi level. Okay, that gives us a very, very easy way of understanding what is happening in the device. Okay, so for that we need to understand this concept of Fermi level very well. Okay. So to do that, let us try to analyze a few situations. The first one we'll consider is what happens to Fermi level in an intrinsic semiconductor. What would you expect? Where do you expect the Fermi level to be? Okay. So in an intrinsic semiconductor, you saw this already many times. You have this electron hole pairs generated, and at a particular temperature, let's say there is some electron hole pair distribution like this. Okay. So what is the probability of finding an electron at EC? What would that be? Well, we saw f of e is basically the probability of finding an electron at E, right? So simply you have to replace E by EC. Okay. So f of EC, and that is going to be 1 over 1 plus exponential EC minus EF by KT. This is the first term. So now, what will be the probability of finding an electron at hole? Let's not consider electron, let's consider a hole. Okay, probability of finding a hole. So a hole at EV. Well, the probability of a hole is simply lack of electron, right? So probability of finding a hole is basically the probability of not finding an electron. The probability of not finding an electron is simply going to be 1 minus f of EV. Right? F of EV will give you the probability of finding an electron. The probability of not finding an electron is going to be 1 minus that. Okay, so this is what it's going to be. And if you, So now, so we have these expressions basically, right? Expressions. So how will this help us find the Fermi level of an intrinsic semiconductor? So we'll use the relation. We know that in an intrinsic semiconductor, N equal to P, right? In an intrinsic semiconductor. We have not added any other dopants. So, conductor basically there's only electron hole pairs which are produced, and that should give us basically n equal to p. So if n equal to p, basically the probability of finding an electron at EC should be equal to probability of not finding an electron at EV. Okay. So basically this relation implies f of EC should be equal to 1 minus f of EV. So this is the probability of finding a hole at EV, and that is equal to probability of finding an electron at EC, right? So this should be equal. That implies you should have, LHS is simply, you have to rewrite it anyway, 1 plus exponential EC minus EF by KT, and this should be equal to 1 minus 1 by exponential, this is basically EV minus EF by KT, right? So this right hand side can be further simplified, and if you can check it out, it will turn out to be 1 by 1 plus exponential, now we'll just flip the sign here, EV by KT. Okay, you can check this. Basically, you just manage work with the fractions and you will see this immediately. Okay, so this is a expression. So what this is telling is this particular relation. This implies that the parameters in the exponential should be equal. Okay, so that means EC minus EF should be equal to EF minus EV. So that will, just rearranging it, that implies EF equal to EC plus EV by 2. Okay. So what this is telling you is that EF, the Fermi level for an intrinsic semiconductor, lies exactly in the middle of the, EF is basically at the middle of the band gap, at the middle of band gap. Okay, so this is the conclusion we have from this analysis. Okay, so sometimes we have various ways of representing. So this is because this is only for an intrinsic semiconductor. We'll actually give it a special name. We say that we'll call it EFI. Okay, so when sometimes we call it EFI. So EF of intrinsic, or sometimes we'll also refer to as EI. EI is basically the middle of the band gap. Okay, so many ways of representing the same thing. All right. So this relation, EF equal to exactly at the middle of the band gap, is almost correct. There is a small catch. I'll give you a problem in the homework which will force you to understand that there is a small deviation because of effective masses of the holes or electrons are different. So there's a small change. I'll give it as a homework. But anyway, for all practical purposes, you can take the EF to be in the middle of the band gap for semiconductor devices. All right. Okay, good. So now we are ready to talk about quantitative numbers of electrons and holes. So far, we have qualitatively mentioned the physics and we said what should happen. Now we are ready to do it quantitatively. To do a quantitative analysis exactly turns out to be a little bit involved. So what we're going to do is take a shortcut. We're going to give you a final result which is applicable in most of the scenarios. Okay? Only when you go to certain very extreme conditions, very, very high levels of doping, then what we are talking about today will not work. But I think that is really not necessary at this stage. Okay? So to understand how to calculate these concentrations, we have to understand two things. One is the Fermi function, which is essentially giving you the probability of finding electrons at various energy levels. And the second thing that we need to understand is what are the available number of states. Okay? We have been talking about these energy levels, right? Essentially, we said this is a band. Essentially, this is a band, and you have energy levels available, right? Energy levels. These are all distributed along the conduction band. And similarly, for the valence band as well, you have a range of allowed levels. Okay. To understand what is the effective carrier concentration, okay. For me, I like to think of it in terms of a classroom. Think of a class, a large class, maybe 100 plus, 200 plus students, okay. and you want to calculate, how many students are there. So that would be something equivalent to calculating the number of electrons in the conduction band. Okay. The way to do that would be, there is going to be always a distribution, a probability of finding students. Maybe the probability of finding students is, high in the front of the class, but as you go towards the back benches, the probability might decrease. There's a distribution function. There's a probability distribution function, and also the number of seats in the tables could be thought of as a number of available states. So if you look at it, the number of benches would be like, maybe 2 students per bench, or 2 students per meter, 3 students per meter, or something like that. There'll be a kind of density of states. Okay, and to calculate the exact number of students in the class, all I have to do is I have to take the density of states and multiply it by the probability function, and then sum it up. That will give me the exact number of students in the class. Okay, we do exactly similar thing here. What we do is we have a function. There is basically a function which is called as density of states function, which gives you the distribution of states in the conduction band and valence band, and then we have to do a little bit of mathematics to actually solve that. So instead, what we will do today is that if we do it exactly, can be a little bit involved. So I'm not going to take that approach. But what I'm trying to tell you is that the carrier density is dependent on 2 things. One is the Fermi function. I'll just write it as Fe. Okay. And number 2, density of states. These are the 2 things that are going to impact your carrier densities. Okay. So instead of doing all that, we will abstract it out and we will introduce 2 quantities here. Okay. You should remember these quantities. So which we call as effective density of states. Okay. So those are the expressions for that is given here basically. So this you see is NC and NV. Okay. NC and NV represent the effective density of states for the conduction band and the valence band respectively. Okay. So with that, you see that it has a bunch of constants, and one of the most important things is the effective mass here. Okay. The effective mass in the conduction band and the effective mass in the valence band. Okay. So if you plug in the numbers, then you get the typical range of this effective density of states, and these turn out to be about 10 power 19. This is the typical range of effective density of states. Okay. But I must caution you here, these numbers are quite dependent on where you take the data from, because effective masses and those are dependent on the experimental procedures. So there can be some variations. If you look at one textbook, it might give you the effective density of states as some number. Another textbook might be slightly different, but they're all going to give you something in the ballpark of 10 power 19 per centimeter cube. Okay, that will not change. So fine, we have this effective density of states. So what is a carrier density then? What is the carrier concentration? What is the concentration of electrons? What is the concentration of holes? To do that, what we will do is we will just simply use the effective density of states and write an expression in this form, N, which is the carrier density. Or if you're talking about equilibrium, okay, let me make a distinction. Let me put N naught. Okay. When I say N naught, I'm talking about equilibrium carrier density. Okay. This is not going to be valid for the non-equilibrium situations. In equilibrium situations, N naught, NC, I will talk about non-equilibrium situations in the next lecture or in the next week. Okay, next 2-3 lectures we will talk about some of those non-equilibrium situations. For now, we are just saying that N basically, N naught when I say it's electrons and equilibrium density of electrons. Okay, so that is equal to NC times exponential minus EC minus EF by KT. All right. So, many times I find that students tend to get confused with the sign in the exponential here. Okay. Let me try to tell you how I remember it. Okay. So, the number of electrons is definitely going to be some fraction of the total number of states available, right? We are saying that the number of states available is basically NC, right? So this is the number of states available. So since your carrier density has to be smaller than this, the exponential has to be negative. Okay. If it is positive, then actually it's going to be the electrons concentration is going to be higher than effective density of states, which is not realistic. Okay, and essentially what we are doing is with reference to the conduction band edge, what is the carrier concentration? Okay, so what we'll say is basically NC is basically EC minus EF. Okay, EF is somewhere right in the band gap. It's going to be somewhere between EV and EC. It is going to be somewhere. So depending on the distance between the EC and EF, we can find out. So for example, let's say if you take an intrinsic semiconductor, okay, basically EF is EC. Let me write it here. This particular thing here, right? This is essentially distance from reference in EV. Okay, that's the thing. Okay, so now let's consider the case of an intrinsic semiconductor. Okay. If you take an intrinsic semiconductor, EF of an intrinsic semiconductor is at EI, right? So basically N0 is going to be NC. NC, let us simply take it as 3 into 10 power 19 into exponential minus EC minus EF is at EI or in the middle of the band gap. So this is going to be minus EG by 2. EG is basically how much? In this case, this band gap is going to be 1.12 EV, and this distance between EC and EI is going to be 0.56 EV. Okay, so N0 is going to be 0.56 EV divided by 0.0256. Okay, that's the KT in EV units. Okay, so if you calculate this, this will be something in the order of 10 power 10 centimeter cube. Okay, and if you remember in the last class, I mentioned that Ni is going to be 1.5 to 10 power 10. Okay, so this is where the slight variations in the numbers come about. The accepted value of N0 is basically Ni is 1.5 to 10 power 10, but there's no harm even if you use simply 10 power 10 in the calculations. Okay? But you have to, in the question generally we mention whether you have to use 10 power 10 or 10 power minus 1.5 to 10 power 10. The answers are going to be close. All right. So you could do a similar analysis for even P. Okay. So N0. So we can also write a similar expression for P0. Okay. So let's say P0 is going to be, now we want to find out with reference to the NV, okay, with effective density of states for holes, which is NV. That's a maximum states you can think of. I mean, it's not exact, but it's a maximum, it's a sort of maximum. So number of holes is going to be something lower than that. So exponential has to be negative. So this is going to be minus, and the distance of EF from the reference level. Reference level here is EV. Okay. So the distance, I want to make sure that this quantity is positive. So I'll write it as EF minus EV by KT. So this is your equation for carrier concentration. Okay. In for electrons and for holes under equilibrium. Okay. These represent, because I didn't mention it, and concentrations under equilibrium. Okay. Okay. This is what it is. All right. So, I mean, you might say that, I pulled the formulas out of the hat. Well, I kind of did. But if I want to introduce the entire density of states formalism, it is going to take me 2 lectures or 3 lectures. And I think that is not necessary at the introductory level. Okay? So, but at least you get the idea that the NC and NV are coming from basically the distribution of states in the EC and EV. Okay? There is basically starting from EC, there's going to be certain distribution, and we make certain approximations and finally come up with these constants. Okay, the effective density of states. Okay? It's as if the density of states is all, all of the states are collapsed at EC. Okay? But anyway, we will revisit that if necessary in the later stages. Okay, all right. So this is how you can calculate concentrations. So now we know what is equilibrium. Okay, let me put this necessary N0 P0. Okay, let me do that. Okay, so what is the intrinsic carrier density? Okay, we know that intrinsic carrier density is basically N0 equal to P0 equal to Ni, right? So I can simply take a product, I can take Ni square is equal to N naught P naught. That is going to be simply a product of these two equations here. So that is going to be NC NV exponential, and I can simply sum up all the terms. EC minus EF plus EF minus EV by KT. Alright. That's going to be equal to NC NV exponential minus EG by KT. Alright. So you saw that, we saw this expression previously when I said that, Ni is going to be proportional to Eg by Kt. In fact, I said it's going to be Eg by 2 Kt. The reason is, now you have to, if you do it, Ni is going to be square root of this, and so there's going to be a 2 here. Okay. So Ni is going to be square root of Nc Nv exponential minus Eg by Kt, 2 Kt. Okay. And this basically a term which we have here, root of Nc Nv, is the constant. In the last class, we said it's exponential minus Eg by 2 Kt, right? When we said the slope can be calculated based on that. So this constant is going to be root of Nc Nv. Okay. All right. So now, before I go forward, I want to use another form of this expression. Okay. Basically, let me rewrite this expression, because while Nc and Nv are convenient, sometimes it's also convenient for us to look at the distance from the Ei. Okay. So what I'll do is this expression formula for n, I'll rewrite it. I'll do it like this. N naught is going to be Nc exponential minus Ec. I'll add and subtract Ei. Okay. So minus Ec minus Ei plus Ei minus Ef. Okay, divided by Kt. So this will turn out to be Nc exponential minus Ec minus Ei Kt exponential. Now the minus will go into the, let me write it that way, just for convenience, I'll take the minus into the terms. So Ef minus Ei by Kt. Alright. So when I do this, I can call this entire term. Basically, you have Ec minus Ei. Ei is simply nothing but Fermi level of an intrinsic semiconductor, right? So I'll call this as Ni exponential Ef minus Ei by Kt. Okay. So what we are doing is here, this is telling you, the reference has changed now. So basically this reference level is Ei. Reference level is Ei. That's why we're saying the concentration of, what is the concentration possible at Ei? It's going to be Ni. Okay. And exponential. So whenever you have a certain amount of doping, it is simply going to, Ef is going to go, we will have to talk about how the Ef changes. But that term actually, for an n-type doping, it will increase. Okay, Ef will be going higher. So this exponential term will actually become positive, and overall you get the n naught to be higher. Okay, and similarly, P naught is going to be Ni exponential Ei minus Ef by Kt. Okay, so I'm just trying to tell you how I remember it. You could also try to come up with your own ways of remembering, but it's essential that you remember these formulas because we will use them routinely. Okay? Come up with any logical approach of remembering this, it should be fine. Okay.